All right, so we're starting the recording halfway into a problem, but not far enough that it's not indecipherable to the viewer. But so here we are. We have d theta dt and dh dt. We know the distance. We've got a picture. We've got an angle. What are we supposed to be doing now? Let's pull out those. If anybody has the notes from the other day when we looked at related rates, there's 2 classes ago. It's like September 29th, I think. I'm not sure. I'm sorry? Yeah, now you see we have dHdt, d theta dt. Well, I'm sorry, we're looking for dHdt, and we have d theta dt.
Go to geometry to find the equation.
All right. Let's see, can we set up a differential formula here? Like, it's some sort of equation that relates all of these guys together. Because remember, you're looking for dH dt, so I usually start with that. D theta over dt, that's good. So now my denominators are all right. Yeah, so now we have to find somehow to get theta out of there and h in its place. So what we're really looking for is some relationship between the height and the angle. And that's where the geometry comes in, okay? You see, so the process is pretty straightforward. We decipher the words, we try to find an equation, we realize what we're looking for. In this case, we needed to get theta out and h in. And now we're going to go to the geometry. So how can this geometry help us? Yeah, you can. And what we have is an angle that is on the unit circle, which is nice. All right, let's look. You see, one of the things I don't think I explicitly said to this class, but I usually tell it to my geometry kids because they struggled more with word problems. They're less experienced with them than you guys are. Take your cartoon and turn your cartoon into an honest-to-God geometry diagram. Obviously, by looking at this cartoon, you can. So let's turn it actually into a real triangle, and that might help us crystallize where our thinking needs to be. So 2 legs and an angle. If I needed the hypotenuse, I would probably be dealing with the Pythagorean theorem in some way. But not, oh, I'm sorry, I should say specifically that that is a right triangle. So can I use something else? Tangent. We're going to go to our trig functions. Whenever you're mixing lengths and angles, you should be thinking about trig. Okay. So from this, I can find out that the tangent of theta, or in this case pi over 4, is my opposite over my hypotenuse, opposite over adjacent. Okay. And actually, I'm sorry, I'm wrong. I'm dead wrong. I should not be putting this in right now because I'm not looking for h right now. I'm looking for dh d theta. And now I need to take the derivative with respect to time on both sides. And I want to be explicit in my notation here because I think that's where some people are getting hung up. So I'm taking the derivative with respect to time on both sides. Okay? And we wind up getting, what's the derivative of tangent? Secant squared. And if I take the derivative of this guy, I wind up getting DHDT, right? H prime all over 500, which is DHDT, right? H prime is DHDT. So now I have an expression for DHDT. Sorry. Wait a minute, hold on. Where's my notation loss? I need DHD theta. Is that where my error is? I don't need to take respect with theta. Yeah, because that's d theta, and my dt's, I'm right. So this is theta prime. And this is, I'm going to see if I can clean myself up here. So this becomes d theta dt secant squared of theta is 1 over 500 dh dt. Remember, theta is a function of time. So that's why when we take the derivative of the tangent, we then take the derivative of the thing on the inside, and the derivative of the thing on the inside is theta prime. So now simplifying, I get 500 times the secant of theta is dh d theta. Because it's algebra. That's the Leibniz notation. That's I take out my time dependence. I don't need the time dependence. They both change with time, but as one changes with time, the other one changes with time. So yeah, if I take away the time, all I'm saying is that how does the angle change when the height changes, or how does the height change when the angle changes? Okay. So now I have what I'm looking for, and let's go back. So you're looking for d h dt. D theta dt, dh dt. And we wanted dh d theta. So this is what I had a moment before. And d theta dt, we have 0.14 radians per minute. And dh d theta is 500 secant squared of theta. So this is 7 secant squared of theta. And the theta that I have is pi over 4. And secant of pi over 4, does anybody remember? Just root 2. Just root 2. Because remember, it's the reciprocal of cosine. And the cosine of pi over 4 is square root of 2 over 2. And this simplifies down 1 all over the square root of 2. This is the cosine of pi over 2. Sorry, yeah, pi over 4. So if I take the reciprocal of that, it's just root 2. And you're done. Am I off by a decimal? I am. That whole multiplication thing. And none of y'all caught me either. It's the morning. I haven't gone through all my coffee yet. I'll be better at flex.
Oh, yeah.
Yeah, we have flex today. Yeah.
So you don't have to solve the first line CH equals to beta, but you had CH equals to CBT.
Mm-hmm.
So I just checked these out.
Where?
That's plot time with CH.
Yeah, now you see that here d theta dt is 0.14 radians per minute. That is me taking a snapshot at a moment. The change in angle right now is 0.14. But the relationship about how the angle changes with respect to time is a function. You see? So right here, d theta dt, when I take this function and I get theta, and I have this right here, okay? This is, this d theta dt, this is a relationship. It's like saying, I'm, here's a way of saying it. I'm falling at negative 32 feet per second squared, okay? That's different than saying, right now, it's moving at 27 meters per second, okay? One of them is an instantaneous rate, and the other one is a relationship between rates. Okay. Sir. Oh, yeah, it's saying how fast is it rising? It's rising at 140 feet per second. I think it's per minute. Units. Yeah, per minute. Huh. Yeah, corner of my desk. Corner of my desk. Let's do another one. All right. This is one I remember doing when I was a kid. Highway chase. Running away from a cop.
Run away from
So we have an intersection. We have a car, police car. And we have somebody, not you, of course, who's in the process of trying to get away. And this is my police officer. That's my blue light special right there, coming to get you. All right. Okay. So you have a cop who is racing towards the street that you are on, and you are racing away. And he tags you with his radar gun. And that's the distance. That dotted line represents the path of the radar gun. All right, and he tags you at an angle like that. All right, now we're going to call this X. Let's call this Y. Now, this we'll call S. That's an S, not a 5. All right, now you are traveling. Oh, sorry. Since he's moving, relatively speaking, he's moving down, right? So, dy dt. We're going to say that the police officer is doing a respectable 60 miles per hour. I know, right? Maybe he's. Wow. How would he stop? Yeah. Um, this ds dt is 20 miles per hour. So that's the distance between the two of you, okay? Because it's going down. It only matters if we care about direction and saying, you know, something is increasing or decreasing relative to his motion or your motion, okay? We're going to say x is equal to 0.8 of a mile, and we're going to say y is 0.6 of a mile. Okay? So he's about a half a mile away, three-fifths of a mile away from the street, and you are 4/5 of a mile away from that intersection, racing as fast as you possibly can, driving like you stole it. Now, we are looking for, if the cruiser's moving at the instant, what is your speed? That's what we're looking for. So we are looking for what? Your speed. How do I express that as in math terms? Your speed. Say again? dx dt. All right. So let's try and set up some kind of possible relationship based upon what we have and what we know and all that good stuff. Okay? Yeah, the Pythagorean theorem. So the Pythagorean theorem says x squared plus y squared equals s squared. Okay? And let's take a derivative with respect to time on everybody, right? So I get 2x plus, now x is a function of time. So I get dx dt plus 2y dy dt.
That's the same thing as 2x times x prime.
Yeah, it is x prime, but we're specifically saying with respect to t instead of saying with respect to the price of eggs in China. You know, I mean, like, you know, x is changing as a function of what? You know? So we have 2s ds dt. Careful. So it looks like a 5 now. It does. It does look like a 5. It's okay. You do know that we're gonna get you for the rest of the year on that one. You know that though. Yeah. Right.
Plug in dy
Yeah. Now you can. Right. So we're looking for this. So let's solve for it. Okay. So we're good so far. And now we have all of this stuff. We just have to throw it in there, right? Do we have stuff? I think we do. We don't have S. S is 1. It's a 3, 4, 5 triangle. It's a 3, 4, 5 Pythagorean triangle. But everything's been multiplied by 0.2. So this is equal to 1. And you can do the Pythagorean theorem to prove that. It would be 0.36 plus 0.64 equals 1. Square root of 1 is 1. So this becomes 2 times 1. And ds dt, I think, was 20. 20. Minus 2y, which is 0.6. And dy dt was negative 60. And this was 0.8. Okay? So before everybody's jumping into huge messes of equations and whatnot, first thing, let's simplify. Take out a 2, right? Yeah, it is fun. Now, you can actually move a decimal point and kill a multiple of 10, but that's all right. Oh. Hey, we don't have any rabbits in this problem. And this was, right? So this becomes positive 36 all over 0.8. So 56 all over 0.8. Excuse me, 560 all over 8, which is 70 miles per hour.
I have a question. Is there a way to figure out how long it would take the cop to catch the person?
Sure. He would, first of all, have to be going faster than 70 miles an hour. But let's also point one thing out. What does he see versus what is reality?
Well, what is reality?
Look, DSDT, when he shoots that radar gun, right, he reads how fast you are moving away from him, right? He's really reading on that radar gun 20 miles per hour because you're off at an angle. If he was straight in front of you or straight behind you, he would be getting an accurate reading. But because he's moving and he's not directly behind you, his radar gun only picks up 20 miles per hour. But in reality, you're really doing 70.
So speed perpendicular.
Well, if he's standing still and he's close to you, like for example, if this is the road that you're traveling upon, right? If that's the road that you're on, if he's here close to the road, then this distance is very close to this distance because the sine of theta is almost theta when theta is very small. Okay? If you look at the sine of 1 degree, right? It's very, very, very small. Okay? And you wind up getting almost 0, right? When you take that sine, if you were to put it and look at it, and if you the sine wave itself, okay? When you're dealing with a small x, then the height of the function, a sine, is not very large. Okay? Its curvature, rate of greatest change, occurs here and there and there and there. Okay? Where it's actually changing the fastest. And we'll get to that. But you would also have to rely upon the fact that the judge would listen to you long enough to, and you would have to be able to explain it. He would be arguing that he was actually going faster than you were. But you could say simply that that the reading was inaccurate. But you're much better off using other legally established means of fighting a ticket.
Not everybody takes calculus.
Right, and I'm not quite sure they teach calculus in law school. So, all right, this is another classic problem. Classic problem. And it's actually quite appropriate for today. No, it's relating to a cone. And we are going to talk about conics today in flex. I've already shown you some of the conics lecture, but yeah, it was last class. So here we have a conical tank, and you know I've seen this problem in different manifestations many times, and I've always wondered just exactly who ever has a conical tank. The only thing I can think of is like a Buchner funnel in chemistry, but really, um, like for example, if you have a little faucet.
That is so tiny.
Um,
I have that faucet in my house.
okay, so we have a conical tank filled with water. It's partially filled. All right. Let's read this off. So try this. As I read this word problem, try to decipher what the variables are that I'm talking about. So, you know, whenever I come across a piece of information, you should write it down. Okay. Water runs into a conical tank at a rate of 9 feet per minute, 9 cubic feet per minute. The tank stands point down, like the picture, and has a height of 10 feet at a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So it's not pouring out. Sometimes the problem has it where it's pouring out. This time we're filling it up. Okay, so we're filling it up. Yeah, right. Everyone's handy dandy. Everyone's got a handy dandy smartboard, right? All right, so let's look and see what those variables were. We have this number. First number we saw, 9 cubic feet per minute. What the heck is that? Well, cubic feet is a volume. dV dt. Okay. The tank stands point down and has a height of 10 feet. So that's H. Let's call that H for height. And a base radius of 5. Not S. Now, um, how fast is the water level rising when the water is 6 feet deep? That is not a G. And how fast is the water level rising when the water is 6 feet deep? Sure, let's call that S.
Where's that 5?
6 equals 5, right, there we go. On a Ronconian clock, right, there we go. So what are we really looking for? Are we looking for height or are we looking for volume? How fast is the water level rising? Height. Well, this is my volume of liquid. You know, this is a constant. This H is a constant, right? It's never going to change. But this is what's changing. ds over dt. All right. Now, one of the reasons why this problem is beloved by all calculus teachers, it's in every book. You go down to McKay's and you open up every calculus book in that section, you will find a problem like this in every single one of them. Hey, don't knock it, man. We all have to do something on our free time. Right. Okay. So we need a relationship of between volume and height. We got to have some radius relationship in there too, because as the height increases, or as you go up, your radius changes, right? If you think about it, as you pour water into this cone, it's going to fill up really fast at the bottom, and it's going to take a long time to fill up at the top. Right, because you're filling up a bigger disk of water, if you think about it. If you think about this cone, it's just a whole bunch of disks of water, right? Like this amount of liquid is not going to be enough to fill that height. You need more of it, right? All right, so, yeah.
Is there a way to find out how long it would take for it to overflow?
Sure. You can find the volume, the total volume of this, which is 1/3 base times height, and then find the relation. I mean, it's just a speed, so it would be time is equal to volume divided by the speed, right? Yeah. You could basically say you find it at 10, and then just put an inequality sign greater than that. All right. So again, you start with a cartoon, right? Now we know that we need some relationship between H and R, right? A relationship between S and H and R and all of that whatnots.
Isn't the area, the area volume of a cone is like
1/3 pi r cubed. Sorry, 1/3 pi r squared times H is the volume of a cube. So the volume of a cone is 1/3 pi r squared H. Okay? But right now we have R's and H's. And if I take a derivative right now, which one is changing? In fact, they both are changing. If I change my volume, my radius changes, my height changes. Yeah? And now all of a sudden I'm going to have to play around with a lot of, I got to do the chain rule, and I don't have a relationship for dr dt. So what I really like to do is get rid of one of these variables if I could, right? So is there a relationship between R and H? What is the relationship between R and H? How?
In order for us to be constant.
You have to find it through that equation.
Well, hold on. Again, we start with a cartoon and we turn it into a geometric object. So this would be 10, and that would be 5, and this is my water level. See what I mean? Mm-hmm. And I now have another small triangle of 6, and what would this be? That's not a 7, it's a question mark. It's 3, how do you know? They're called similar triangles. So R and H, right. So H is equal to 2R, or R is equal to H over 2. You see, so now I've gotten rid of R's. because they're proportionate, because you have similar triangles. So 5 over 10 would equal x over 6. Right. Yeah. Good question. Yeah, it's always going to be, because of the angle that we picked, right?
Yeah.
It would always be half as much.
Just like, cutting into the same.
Right. Exactly. Because they're parallel. I mean, this segment, the height of the water, is always going to be parallel to the rim. So, whoops.
Consider the meniscus.
We're not near the top, and we also don't.
No, meniscus
Oh.
is throughout.
Yeah, but when you measure a liquid, you're not going to be caring very much about the meniscus at that point, simply because the surface tension is negligible in comparison. All right, so we can simplify my equation. And you see my S that I gave it is really just a height, with a much funnier name.
Like where it's here.
I hope no.
Oh, not the H.
They're probably gonna watch the lady next to me.
Probably have one guy who's like this.
Yeah, it was in the
I want to see that so bad.
Wait, where's the
The 2 squared times the 4. I'm sorry? Times 3, yeah, the 4 times the 3. Sorry. And we are really now, we can kind of get ourselves out of this abusive variable situation. Whereas h prime is the height that I give a crap about versus.
Can you go back down real quick?
And I can simplify, of course. What am I really looking for? I'm looking for dH dt. And we have dV dt. So this is what we're looking for, right? So dH dt is equal to 4 over pi h squared dt, and the reciprocal of dV dt. Actually, no, dV dt. So I just moved everybody over to the left. I did.
Yeah, dividing inverse. But why did you take the reciprocal of
Okay, hold on. All right, chill. This reduces. Everybody chill. Do we all agree? Do we all agree with that? I just turned it around and simplified my fraction. What do you mean?
okay, you move DH to okay, DH is D times 3 pi over H.
Yeah, I just reduced my fraction. Right? I reduced my fraction and turned it around.
And then when he does dH over dt, he has to divide it by that by pi h squared over 4, so you multiply.
Good job. Not bad.
and dVdt was some 9. Right? Which just equals 1 over pi. Yeah. I took the derivative. Oh, no. Here, from here to here, I squared the h, and then I squared and then I multiplied the h to the. I just cleaned that guy up a little bit.
Yeah, you kind of sometimes.
Algebra. Yeah. Algebra. It's actually where the word comes from.
Sounds like a.
That's the Arabic word for reunification. It's where the unknowns on both sides reunify onto one side. That's where it came from. And it was developed.
Non-Greek.
Al-Khwarizmi was the guy who wrote the first book on it, and that's where we get the word. That's where they get the term algorithm. Al-Khwarizmi. And yeah. And if you needed to approximate 1 over pi, it would be pi is approximately the square root of 10. So this would be approximately 1 over the square root of 10, which becomes the square root of 10 over 10, which is approximately pi divided by 10. So 0.316, roughly, or 0.314, roughly, in that range.
You know so much.
All right, you good? All right, next. All right. I think there was a problem related in your homework that dealt with a falling ladder. So we have a 13-foot ladder is leaning against a house when its base starts to slide away. All right, so we have a ladder leaning against a house. It's 13 feet long. Today it is. All right. That's my x. That's my y. That's my theta. Yeah, we can assume that it's a properly constructed house. It is a geometrically correct house. All right, by the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. Did I ever get those right? Yeah. All right. And again, because as this thing slides away, it accelerates as it falls. So the y is going to be going down, and the x is going to be increasing. dy dt is going to get bigger. It's going to be positive. And ds dt is positive because it's growing. Right. So what do we have? We have a triangle. Let's turn it into a real triangle. And Does anybody remember the second smallest primitive Pythagorean triple? 5. Right. Yeah, the 5, 13, 12 is the second smallest. Well,
I didn't know that part.
mm,
Is it 60, 50, 90, or no?
no, not necessarily at all.
Sorry, not 60.
No, you're thinking 60, 30, 90.
Yeah.
No. 60, 30, 90 has a ratio of 1, 2, square root of 3.
Yeah, yeah.
Yeah, it's not that.
Oh,
That's just a Pythagorean triple. All right, the question, there are 3 parts, A, B, and C. Part A, how fast is the top of the ladder sliding down the wall then? So what is that going to be in terms of equations? Vivian, give me that. What do you got? The top of the ladder falling. Yeah.
It's your Y and this is your X. So just one
X.
the Y or X.
Yeah, the question is how fast is the top falling? No, relative to time. We might. We'll see well, in the beginning, you're just trying to find all of your parts. And then you can say to yourself, all right, well, what are my intermediate pieces that I might need to care about? Okay? So, what is my geometry telling me I should be caring about in this particular part? No. I mean, like, the geometry. Should I be using trig? Should I be using what?
Oh,
Pythagorean theorem. Okay? Because they're not asking me about my angle. Maybe B or C talks about the angle, but not right now. All right, yeah, part C deals with an angle. So we have x squared plus y squared equals s squared. And now, no, the top of the ladder is falling at 5 feet. It's almost on the ground, because remember, it's a 13-foot ladder, right? So go ahead and roll this out. I think you guys can at least get the next step.
yeah, we solved this stuff.
Try to get the next step on your own. When we come in for second flex, you could finish this, but maybe you could get started on it. The answer key is down here. If it's perfect, mark it with a check. If it's not, just leave it alone. I'll take it. The parallel line stuff. Okay.
The first block and they're so
Great.
I mean,
All right.
they're both in sports.
Okay. So, how did this go? Take the derivative with respect to t on everybody. Now, what about that? Well, if we did take a derivative, it would be 2s ds dt. But what is ds dt? How long, what is s? S, it's a constant, right? The length of the ladder doesn't change. So ds dt is 0. S squared is a constant.
Then why do you have at the top DS plus 5T?
I should say dx dt.
Oh, God. Daddy.
So this is 0. Right. X dx dt plus y dy dt equals 0. And I just divided that at 2. And what we're really looking for is dy dt, right? So I'm going to blow Colnita away. So now dy dt is equal to negative x over y dx dt. And dx dt was a constant. We knew that, right? That was 5. And x and y we know, right? Feet per second. Okay, now you guys, I gave you guys homework already. It's posted. But an interesting problem, okay, would be the next part of this question, which says, what is the rate of the change in the area of that triangle? So now instead of the Pythagorean theorem, you're going to be using the area of a triangle formula. Okay? It's a good problem. I'll see everybody in.
What was this episode of the Ronco Show brought to us by?
This episode of the Ronco Show was brought to you by DSTT. And the number 5.